Hi, my name is Carson Ward, and today we're going to look at CLIK on PLCs, attacking control logic with decompilation, and the use of a virtual PLC. Now, CLIK stands for Control Logic Infection Attack. It's a remote attack on control logic of a PLC and industrial control system. The goal of CLIK is to introduce malicious logic in a target PLC automatically and hide the infected control logic from engineering software or control center. The primary exploitations from this work include a zero-day vulnerability against the PLC's password authentication mechanism and employing a virtual PLC to intercept and engage with engineering software. Now in this environment, the PLC is behind an ICS, or an industrial control system. ICSs are essential in the automation of physical processes, such as wastewater treatment facilities, power grids, nuclear power plants, and gas pipelines. Now there's a relationship between field sites and control centers. Now the field sites are actually hosting PLCs. That's where the PLCs are located. And these PLCs are interacting with sensors and actuators to carry out these physical processes. Increasing connections to corporate networks pose many pros and cons to the situation. Some pros include allowing more information on control systems performance, such as historians, which could be used to trend data over an amount of time, or remote monitoring. But also as a con in this situation, there's a vulnerability to cyber attacks. Many PLCs running today are legacy devices that possess several attack vectors. In fact, the PLC looked at in this implementation is a legacy PLC, and its attack vector will be investigated. So a system can really only be as secure as its weakest link. Isolating critical components could prevent exposure to unknown vulnerabilities. There are several attack vectors at play with CLIK. They attack authorization, the fact that the PLC is not isolated, and the fact that this is a zero-day vulnerability. There's nothing that has been done to patch it. It's unknown by the vendor and the user. Now the CLIK attack is initiated after an attacker has penetrated into an ICS and communicated successfully with the target PLC. Basically, at this point, comprising an ICS is out of the scope of this work, so we're going to assume that we are behind the ICS and can communicate to a PLC for this implementation. So the attack chain of CLIK comprises of 4 phases. The first phase is stealing control logic from the PLC, which is subverting security measures to gain access control, retrieving the logic from the PLC, which is going to be retrieved in a raw binary format. And in phase 2, there's decompiling the stolen binary to source code, basically just changing it into a format that's more easily manipulatable. And in phase 3, there's infecting the control of the PLC. In this phase, there's going to be rule-based malicious modifications, and those modifications are going to be compiled back to binaries and sent to the PLC. And the last phase is concealment of the infection from engineering software by the use of a virtual PLC. Now this virtual PLC is going to intercept traffic between the infected PLC and the engineering control software to make the infected PLC appear okay. Now in phase 1, stealing the control logic, this includes compromising any security measures that are supposed to protect the PLC against attacks. These measures include integrity protection, access control, and in this case, authentication. Any comprised security measures or combination of them can ultimately grant an attacker read-write access. Any of those apply to this phase. In this implementation specifically, CLIK is going to focus on a zero-day vulnerability found during its implementation. Now, to have a closer look at this zero-day vulnerability, we're going to start looking at this where it's focused on this authentication mechanism through the PLC that's provided by Schneider Electric Modicon, and the model is an M221 PLC. It's also used with its engineering software, which is SoMachine Basic. This zero-day vulnerability pertains specifically to just a few firmware versions supplied from the vendor, and they've since been disclosed and mitigated. Now, remote reading from the PLC is not allowed without authentication, as it should be, though there is a problem because remote writing is allowed, and that's a vulnerability that will be exploited. Authentication between the PLC and its control software depends on verification of the PLC password. The password is stored as a hashed password on the PLC. Now, the hashed password could be overwritten by exploiting that remote write access vulnerability, though the challenging part would be locating where the hashed password is stored in memory. So just a brief overview, let's look at the authentication process between engineering software and a PLC. So on the left, we see that engineering software is going to send a request to the PLC. This mask is going to be sent back. It's going to be masked again with this authentication request, including the masked hash password sent to the PLC. Essentially what's happening is, as long as the password that the engineering software sends matches the one that's hashed inside the PLC, it's going to be granted authentication through this response. Likewise, the CLIK process follows the same procedure, though it includes two additional steps where it's actually writing a new hash into the PLC, and based off of its authentication request, we'll know whether or not the authentication worked or not. So the idea is we're going to write a new hash into the PLC, and if that hash writes directly over where the original hash existed, then the PLC is going to grant CLIK access into the PLC, or more specifically, read access. So determining location of this password hash comes down to the findings. Now, the hash location has been found to always be preceded by some variable size zip file which contains metadata, and the zip file is mapped to the static address D000. The code block of the control logic, which is stored in machine code, is always mapped to an arbitrary location starting at the address E000, and there's referred to as a random gap between E000 and the code block itself. Now, the password is generated as a SHA-256 hash, which is known to be 32 bytes long. The challenging thing here is that the zip file is of unknown length. We know the password is after this zip file, but since CLIK doesn't have any read access, it doesn't know the actual size of the zip file. Therefore, it doesn't know the actual location of this password hash. Though it has a general idea, it needs a specific model to understand where this new hash needs to be inserted in order for this exploitation to work correctly. So identifying this password is still really challenging. There's several different methods, which could include needing to know an offset from a known reference point to the password hash. Basically, if there's a known reference point off this password hash, there could be a known offset to get to the password itself and overwrite it with a new one. Unfortunately, this scenario offers no known offsets that are consistent, so that way won't really work. So additionally, there's another method which would include filling memory between the zip file and this random gap here at E000, but you are going to overwrite the password, which you intend to do, though you could also overwrite information inside the zip file or this metadata, potentially corrupting the PLC, definitely corrupting the zip file. Now, an approach used to overcome this challenge employs an iterative search algorithm, which creates a new hash and inserts this hash starting at the address E000, or rather, it's ending at the address E000. And after this new password hash is inserted, it's going to send an authentication request. If that authentication request fails, then CLIK knows that that is not the location where the original hash was stored. Once it knows that the new location has been diverted, it's no good. It's going to negatively iterate this new password hash up this memory table. Once the new hash matches the exact same position as the original password hash, at that point in time, the PLC is actually going to grant the CLIK access into the PLC. So once security measures are now compromised, CLIK will communicate with that PLC using the PLC's supported protocol, requesting a transfer of the control logic. CLIK will first obtain the configuration blocks, which are just blocks that contain metadata, and it's very useful to get valid information on other blocks, which are data and code blocks. This metadata just makes it a lot easier to understand how to map memory and data within these additional blocks. The control logic is now retrieved and understood. So now on to phase 2, which is decompiling the stolen binary to source code. The stolen source code is still in binary format, so it needs to be decompiled from this binary format to source code, which allows the infectious phase of CLIK to be automated. Now these source code languages could be ladder logic, structured text, function block, or in this case, instruction list, or IL. Now, how it's actually executed, the decompilation, is code blocks are used as input, which come into this decompilation process. They're sent to a mapping database, which is actually defined a standard IEC 61131-3 for decompilation. And we'll see a little bit more of a better demonstration on how this works in a following slide. But essentially, these code blocks come in and instructions come out into source code, and this source code is easily parsable and manipulatable, which makes the infectious phase a lot easier to implement. So here's just a more detailed overview of what's happening behind the mapper. Machine code comes in, and out comes these instruction list source code instructions. So I included this ladder logic example here, which is just the same thing that's going on with this instruction list instruction. It's looking for to examine if closed memory addresses, or actually these are input addresses. Once they're both engaged, then this OTE is going to be energized. So essentially, if these two inputs are true, if they're on, then this is going to turn on. This could be a start button in some sensor that turns a motor on. And likewise, the second rung here that's evaluated is just a single input, which is actually a memory address, which goes to an output of a memory address. So this could be if some button on an HMI touchscreen is clicked, then this memory address here might be mapped to the visibility of some other control, for instance. So this is just kind of representation of what's kind of happening under the hood with this logic here. And what's really happening within CLIK is it's creating this right here, which is the IL instructions. And this is what's going to be parsed through in phase 3. So in phase 3, there's the rule-based approach to inject this malicious code. Now there's 5 rules. Some of these rules include inputs and outputs are replaced with memory bits. Rule 4, for instance, replaces operators found in equations. So if there's, say, like a greater than equal to that's comparing two values, it could be replaced with a less than operator. Additionally, in Rule 5, it states that they're going to insert a new rung at the end of logic with an energizer output of a target actuator. And just to better visualize that, I also included this, which let's just say there's some input that they found that goes to this target actuator. Now, this target actuator would not be green because this input wouldn't be on. Let's just say green is on. But since this new rung has been implemented or been appended to this branch, it goes directly to this target actuator, which is actually bypassing whatever this input is, and it's just turning that actuator straight on, bypassing the original logic entirely. Now this could have very severe outcomes, which could lead to very dangerous situations where Something, a dangerous motor could be turned on clearly when it's not supposed to, or maybe some alarm indication light isn't being turned on when it's supposed to, putting people in harm's way. So just a continuation of phase 3, once the malicious code has been injected into the source code, it's then compiled back down to binary using the same database as before, except it's just a reverse process. It's now converting machine logic, or rather it's converting source code into machine code. And the infected binary code is then sent to the target PLC. Just an example over here on the right, you can see how the mapping is worked. So once it finds a corresponding ladder logic, it then can map it to its respective machine code logic or machine code. So in phase 4 is the concealment of the infection from engineering software. This is implemented through the use of a virtual PLC. Basically, it achieves stealthiness by avoiding significant perturbation in an environment. It utilizes captured network traffic from phases 1 of CLIK to engage engineering software. There's 2 main challenges faced with the virtual PLC implementation. The first one is when engaging software, when engineering software sends a request, the virtual PLC has to identify the corresponding response message based on captured traffic. Now, what that means really is when engineering software is communicating to the actual PLC, the virtual PLC is going to intercept that response or the request, and based on some reconnaissance that it did in phase 1, it's going to pick the correct response message to send back to that engineering software to make it look like the normal PLC is talking to it just as it always has been. Now, in the second challenge, there's the dynamic fields of responses that values will vary across sessions. This is very challenging to overcome, and it's been mitigated through the use of dynamic field formats. Before getting to that, just want to touch briefly back on these 2 challenges. First is the communication template, which is comprised of this request response pair. Now, this is based on insight that there is a manageable number of different messages between engineering software and the PLC. And when the virtual PLC receives a request message, it uses this template, similar to a lookup table, to find a matching response and reply with that matching response. Any requests that are not on this template are considered to be control logic messages, which then the virtual PLC can actually refer back to the original extracted PLC data logic and give messages back to the engineering software based on that. Now, for that dynamic field format that we were talking about earlier, it has to take into account values that may change, such as like a session ID. It does this by analyzing a large amount of messages from packet captures, and some dynamic fields can be inferred by observing change between messages. So let's say we're looking at messages that are known to be associated with a large chunk of data, and that could be used to identify, say, like a sequence number, because we're going to follow that packet sequentially and look for the change between these messages. Such things as the sequence number, session ID can all be inferred through very intensive analytics of these packages and messages. So putting it all together, it comes down into all 4 phases, where phase 1 is stealing the control logic from the PLC in its binary format. It's going to then, in phase 2, decompile the stolen binary into more manipulatable source code. This source code is then used in phase 3 by using the rule-based malicious logic generator, which, based off of the 5 rules that we stated earlier, is going to generate malicious logic. Once that logic is generated and inserted into the source code, it's then compiled back down to a binary and transferred to the PLC as malicious logic in binary. At this point, phase 4 takes place. Phase 4 is going to intercept that traffic to and from the target PLC, and the engineering software is no longer going to be able to talk to the original PLC. It's only going to be able to talk to the virtual PLC. And in this case, the target PLC has been completely compromised and unreachable from engineering software. Engineering software has no idea that the PLC has been infected, and from its viewpoint, everything looks totally fine. So just as an analysis of the results, now CLIK was evaluated on real hardware, real software, on over 52 different control logic programs stored on the M221 PLC. Each program contained a strong 25-character password, and the overall performance was very successful. CLIK actually had 100% success rate in every single measure. Every single time, the password algorithm worked perfectly fine. Every single time, the decompilation and insertion of malicious code worked every time. Based on these metrics, you can see that in these example programs, they provided an example traffic light, gas pipe, and hot water tank program. The original logic is actually very similar, and in the case of the gas pipeline, it's the same size. And the overall success is by and far perfect. It's 100% successful. Now, this success, in this case, solely depends on the security breach that they were able to take advantage of with the zero-day vulnerability, though any security vulnerability could be used in this approach. It doesn't have to be that specific one for the M221. Countermeasures to prevent a CLIK attack include two main countermeasures. The first being control logic verification, which is comparing the control logic being transferred with the original control logic. A lot of control logic software suites or engineering control logic software allow side-by-side comparisons, rung for rung, instruction for instruction. It's a very tedious process, but it could technically be used to prevent an attack like this. Now, the more useful countermeasure would be control logic detection. This is similar to an IPS. It's actually just detecting and blocking the transfer of control logic packets on an ICS network unless that transfer is explicitly granted. Basically, an engineer would have to request access to this, be approved by somebody else, and all that traffic is going to be monitored. This basically prevents any autonomous actions from CLIK that would be happen, which obviously would not be granted. So other solutions, just having isolated zones. Isolated zones could prevent things like zero-day attacks, because zero-day attacks obviously are not known by vendors or the users, and by isolating old legacy PLCs, these zero-day vulnerabilities can be less likely to occur, especially remotely. Hardening. So when these zero-day vulnerabilities in the case of this implementation are discovered and patches are released, those patches need to be applied to these devices, which will harden them against possible attacks. And finally is an IPS, which can prevent any intrusion, very similar to the control logic detection mentioned before. So as a conclusion, CLIK is a type of remote attack that targets PLCs on a compromised ICS to disrupt an automated physical process. It's a full attack chain which was shown to successfully be implemented on a real PLC, in this case the Modicon M221 PLC, and engineering software, in this case the So Machine basic engineering software. CLIK was implemented with the use of a zero-day vulnerability in this case. This vulnerability took advantage of the authentication to grant read and write privileges to the target PLC. The control logic was abstracted from the PLC, inserted back with malicious code, and additionally, CLIK was able to hide the infected PLC by employing a virtual PLC to engage with the engineering software using acquired network traffic from the original control logic. Vulnerabilities found from CLIK have since been mitigated, though similar attacks could be avoided with well-defined ICS traffic rules. Thank you.